Hello. Today we're going to take the derivative of a multivariable function with its variables as functions themselves. First, let's apply this differential operation and expand the expression to the definition of a derivative. This difference is what we're going to focus on. It is just the infinitesimally small difference of f of xy. We just multiply the dt out. We'll bring the dt back after some rearrangement. Let's now add these two terms that will cancel each other out to still be 0. So we're just adding 0 and we haven't really changed anything about this expression. Let's now rearrange this expression by swapping these two terms. Let's call this red term g of x of t, and we'll note it up here in the corner. Note that the only difference between this term and this term is this h. So let's rewrite this term as g of x of t plus h. Now we're going to reintroduce the h and divide the entire expression by dt, also known as h as h approaches 0. This term is just the derivative of g of x of t with respect to t. Now you're taking the derivative of a function of a function. We have a rule for this already called the single variable chain rule. That I'm going to write above here. But refer to note 1 again, and we'll see it is just the partial x of f times x prime. The h disappeared in y when we applied the limit, so note it simply as y or y of t. We can apply the same logic for the second term to get the following result: partial y of f times y prime of t. This is the multivariable chain rule for two variables. Let's try this out on an example. Our example in this case will be x squared times y cubed, where x is equal to sine of t and y is equal to e to the t. Let's now take the derivative, recall the double variable chain rule, and so we can write this expression in terms of y and x. We can apply the substitutions listed in the vector below to write this expression in terms of t. This is exactly what we get if we made a substitution in the beginning and took the derivative directly without using double variable chain rule. We could just use product rule and single variable chain rule instead to get from this expression to that expression. So why do we care? What is the point of applying this rule when we already have the expression in terms of other functions? That is a valid sentiment to have, as I've asked myself that. Well, there are some reasons. For starters, it is a somewhat good shortcut once you get used to it. We don't have to apply several rules to get the same result. This rule can be used in differential equations and other problems where we have functions as unknowns, since beware that in this example we have everything predefined for f, x, and y. This may not necessarily be the case in every situation. We need to think of the double variable chain rule more as a theorem than a rule, which brings me to my final point. This theorem has many implications in other areas of math, as well as physics. The entire point of this example is to see if this theorem actually works, or I was just talking hot shit this whole time. Now that we have been acquainted with the double variable chain rule, what would the chain rule for 3 variables be? 4 variables? Screw it. Let's say we have n variables, noted by this vector x up here. Like we did before, let's focus on this very small difference of f and divide by h afterwards. We are now going to add these bunch of terms where the green terms cancel off the red terms to be still 0. These terms follow a pattern where we take h away from each variable starting from the first x1 of t. The first row has x2 of t plus h, which will become x2 of t in the second row. The second row has x3 of t plus h, which will become x3 of t in the third row, and so on. Let's rearrange this expression by bringing this term from the original df down here so the pattern is satisfied. We'll just shift this right column up, and by now you might already see where we're going with this. Let's divide this entire sum by h. If we're applying the single variable chain rule on each row of the sum, we get the following: partial x1 of f times x1 prime, partial x2 of f times x2 prime, partial x3 of f times x3 prime, and so on. let's try making this sum look prettier by writing it as a dot product. This dot product can be further simplified with notation gradient f dotted with vector x prime, where gradient f is the vector that contains the derivatives of f with respect to each variable, and x prime is the vector that contains the derivative of every variable. And so, this is the final result. The generalized chain rule of a function with any amount of variables shall be gradient f dotted with the derivative of its variables. For those that are still watching, I have a proposal for you. Grab a piece of paper and try doing this. You can actually prove product rule using chain rule, multivariable chain rule that is. Because product between two functions, h of t, g of t, that's just a function applying to those two functions. They're just variables in one big function, let's say f of hg. That's all. So you can use multivariable chain rule to prove product rule.